Welcome to Calculus. Today we will investigate how to integrate rational functions using partial fractions. We'll take a look at 4 examples. Our first example doesn't involve integration. We're given a function r of x that's a rational function, x cubed plus 3x minus 4 divided by x minus 2. Our task is to write that improper rational function as the sum of a polynomial function and a proper rational function. What we've got to note that's making this an improper fraction is that the high power in my numerator, which is a cube, exceeds the high power in the denominator, which is a power of 1. Whenever I've got that arrangement and I've got the task of integration in view, I need to run polynomial long division to reduce this down to a single polynomial plus a fraction that has a power in the numerator that's smaller than the one in the denominator. So we want to run polynomial long division. So I'm going to set that up over here on the right. And recall, I'm going to put the numerator in the division as the dividend. So I'll put x cubed plus 3x minus 4. Now, I see I'm missing a squared term. I need to represent it with a placeholder 0. So I'll put plus 0x squared. I'm going to place the denominator as the divisor out here on the left. So x minus 2. And then I want to divide. So recall, when you're doing polynomial long division, really where we need to focus are the first terms, inside, outside. And that's what I want to divide first. So I'm going to divide x cubed by x to the power of 1, and that's going to give me x squared. So that's the first term in my quotient here. Now, once I've written it, I need to multiply back times my divisor. Now, there's 2 terms there, so it's going to be x squared times x. That's x cubed. That should match with what's above it. We want it to cancel out. And then x squared times negative 2 is minus 2x squared. At that point, I'm ready to subtract. And again, my first term should cancel. X cubed minus x cubed goes to 0. And then for my second term, I need to be careful because I've got a minus on the outside of the binomial that needs to distribute to the second term. So this is going to be 0x squared from the dividend plus 2x squared. And then I will carry down the 3x. So we've completed one full cycle. Now we're going to start the division a second time. 2x squared now divided by my divisor, just x. And that's going to give us 2x. So again, I'll place that as my second term in my quotient, and now multiply back. 2x times x is going to be 2x squared. And again, that's going to cancel, so that shows me that I did the division correctly. And then 2x times negative 2, negative 4x. I'll subtract. Got a cancellation from 2x squared minus 2x squared. Then we've got 3x minus negative 4x. That's going to be plus 7x. And then I'll carry down my last term there, the minus 4. That completes a second cycle. Let's complete it with this last division, 7x divided by x, and that's just 7. So that concludes my polynomial part of my quotient. What we got to find now is the proper fraction, which in other words is the remainder. So I'm going to multiply back. 7 times x minus 2 is 7x minus 14. I will subtract. First term cancels. And then negative 4 minus negative 14 is plus 10. So I will finalize my quotient here by putting plus 10 divided by the original divisor, x minus 2. And what we've got is an equivalent form for my r of x function, x squared plus 2x plus 7 plus 10 divided by x minus 2. So for this question, we didn't have to integrate quite yet. We're just practicing rewriting an improper rational expression as a polynomial and a proper rational function. So on our second example here, number 6, I actually want to do that same process and then integrate from there. So again, I've got the integration of x squared plus 4 divided by x minus 2. And the telltale signs that I need to run polynomial long division is that my high power in the numerator 2 is bigger than the high power in the denominator 1. So anytime you've got the high power in the numerator, you want to do this polynomial long division. We'll set it up. The numerator goes inside as the dividend. I'm missing a linear term, so I'm going to put the placeholder plus 0x plus 4, and then x minus 2 outside as the divisor. Now I'll divide x squared divided by x is x to the first, so I'll place that over x to the first term in my quotient. Now I'll multiply back. X times x minus 2 is going to be x squared minus 2x, and then I'm going to subtract. That's going to give me 0 from my first terms, and then 0x minus negative 2x is plus 2x, carry down the 4. And we're ready to divide a second time. So I've got 2x now divided by my divisor term x, and that's just 2. So that completes the polynomial part of my quotient. I'm going to multiply back. That's 2x minus 4. We'll subtract, and again, first terms cancel. 4 minus negative 4 is 8. So my equivalent version of the x squared plus 4 over x minus 2 is going to be x plus 2 plus 8 over x minus 2. So we'll substitute that in here, and then we want to actually integrate. So it's the integration now of x plus 2 plus 8 over x minus 2 dx. So you can see by rewriting these improper rational expressions, they become much easier to integrate. So at this point, I've got now integration of just x. That's going to be 1/2 x squared. Integration of 2 is plus 2. And then thinking about 8 over x minus 2, I'm going to just take that 8 as a coefficient off to the side. So really what I'm thinking about is 8 times 1 over x minus 2. And remember, if I've got 1 over x minus 2 as my differentiated version, my antiderivative is going to be the natural log of x minus 2. And that's going to complete this. So not plus there, that's times. So it's 8 times the natural log of x minus 2. And at that point, what I want to do is put a plus c, since that's an indefinite integral. And that's, at that point, complete. I'm missing one part. I see I didn't integrate 2 correctly. That should be 2x. And that completes it. 1/2 x squared plus 2x plus 8, natural log, absolute value of x minus 2. So the strategy of dividing when I've got an improper rational expression simplifies the integration. That's the rationale behind that strategy. Well, let's take a look at another rational integrand. Here I've got the integral of 1 over x minus 2 times x plus 1 dx. And if I check here, I do not have the same arrangement where the high power is in my numerator. My high power on this example is in the denominator. It's a little tricky to see because the denominator is factored, but I've got an x to the power of 0 in my numerator. So just thinking about what my power is, it's a power of 0. If I were to multiply this out, this would be x squared minus x minus 2. High power in denominator is 2. So for this example, I wouldn't want to run polynomial long division. It wouldn't be able to do anything for me. But I do need to simplify this rational expression. And the way I want to do that is by creating partial fractions. So the way I'm going to set that up over here on the side is I want to take the original expression 1 over x minus 2 times x plus 1. And I want to rewrite that as the sum of some fractions that contain individual factors in the denominator. So my first fraction I'm going to call something over x minus 2 plus my second fraction something over x plus 1. And the somethings I'm just going to mark with variables a and b. And I need to come up with those values. Those are numbers. So to do this, the strategy is to take and multiply by the LCD, the least common denominator. So that happens to be x minus 2 times x plus 1. So I'll multiply that by here on the left. It'll cancel out. I also want to multiply each term by the LCD on the right side. So I'm going to have a cancellation with my first fraction. It'll just leave one binomial. And the same we'll see here with my second fraction on the right. And that gives me this version now. 1 equals a times x plus 1 plus b times x minus 2. So at this point, I want to solve for a and b by choosing some convenient x values. By convenient, I'm looking for x values that will cause a 0 cancellation by addition or subtraction. So if I want to cancel out the b term first, I'm going to choose x equals 2. So let's see why that's going to help us. That's going to be 1 equals a times 2 for x plus 1 plus b times 2 minus 2. And that 2 minus 2 becomes 0 times b. That whole b term vanishes. What I can do now is solve for a. This is 1 equals 3a. If I divide by 3, I get the a equals 1/3. So one of these is now solved for. Now I want to solve for b in a similar way. So again, I'm going to choose a convenient x value to cancel out the a term. That's going to be x equals -1. So just like we did previously, I'm going to select my x value, then substitute it in. And that's going to give me 1 equals my a term there is going to cancel out because -1 plus 1 is 0. 0 times a is 0. That's going to equal -3b. By division, b equals -1/3. So that lets me rewrite, heading back to the integral here, the integrand as the sum of two fractions. So it's going to be the integration of 1/3 over x minus 2 plus -1/3 over x plus 1 dx. And at that point, that really simplifies the integration. Those are set up to integrate now back to the antiderivative of natural log. So I'm going to go ahead and do the integration. I'm going to let this 1/3 come out front just as a multiplier. So 1/3 times, so if I've got 1 over x minus 2 dx, and I'm looking for an antiderivative, that's going to be the natural log of x minus 2. And I'll let the same happen here with my -1/3. I'll let that set as a coefficient out front. And again, this is also set up for natural log. If I've got 1 over x plus 1 dx, the antiderivative for that's going to be the natural log of absolute value x plus 1. And with that strategy in place, I can complete the integration. Because it's indefinite, I will put the plus c, and that's complete. So in this example, I had two factors in the denominator. Both were linear, and they were distinct. They were unique from each other. Our last example contains an irreducible quadratic factor. So just thinking about my two strategies that we've used, I've used polynomial long division if the power in the numerator is higher than in the denominator. That's not going to work here because I've got, again, x to the power of 0 in numerator. I'm not sure on this whole polynomial, but the highest power is going to be a 3 in the denominator. So because the high power is in the denominator, I can't divide by polynomial long division, but I can use the partial fractions strategy. Now I have to take a slightly different approach because I've got a quadratic in the denominator and I cannot factor it any further. So x plus 1's like my previous linear terms, x squared plus 4, that's the irreducible quadratic. I cannot factor x squared plus 4 in the real numbers. So as I set up the right side, the first term will look familiar, a over x plus 1. But for my second term, x squared plus 4, I've got to include a binomial with two coefficients b and c. So it's going to be bx plus c. And I want to do that because I need to have my power in the numerator be 1 less than the power in the denominator. So let's set up our partial fractions. Again, I'm going to multiply each term here by the least common denominator, which is x plus 1 times x squared plus 4. So just like in the previous example, this left side will cancel out. I'm going to see individual cancellations here on the right. X plus 1 is going to cancel, so there I leave x squared plus 4. And then x plus 1 will stay on the second one, x squared plus 4 will cancel. So what we're going to try to solve is this. 1 equals a times x squared plus 4 plus bx plus c over, bx plus c as a binomial times x plus 1, the factor that did not cancel. So for this example, I can choose one convenient number that would cancel out one of these groups, A or B and C. And I'm going to choose x equals -1, just keeping in mind that I can cancel x plus 1 if I plug in -1. So we'll set it up here. I'm going to write everything in red, then we'll substitute in my -1. And just as before, I'm keeping in view for cancellations. That's really what I'm looking for. So now let's substitute in -1. So -1, -1, -1. And my cancellation is going to be here on this second term, the one with the b and the c. -1 plus 1, 0. 0 times that whole binomial will cancel it. So what we've got is 1 equals, if I multiply out here, -1 squared is +1 plus 4 is 5. So that gives me 1 equals 5a. By division, a equals 1 over 5. So now when I go to solve for b and c, what I want to do again is choose a convenient value to plug in for x. And so what I want to do is cancel out this b term. So I'm going to choose for the next version x equals 0. So I'm going to set it up again, and then we'll plug in our 0. At this point, I can plug in my value for A. So I'm going to put a fifth there, and then I'll set up 0 squared plus 4 plus B times 0 plus C times 0 plus 1. So we'll fit in our zeros there. 0, 0, 0. And let's simplify and solve here. So this becomes 1 equals a fifth times 4. 0 squared plus 4 is 4. Plus my B times 0 is going to cancel. And then it's going to be C times 1. So just plus C. And that's going to give me an equation. 1 equals 4/5 plus C. If I subtract 4/5 from 1, C also has the value of 1/5. So I'm going to box these as we go. So we've got 2 of them. All we need to do now is come up with a third value. We need to solve for B. So what I want to do now is I want to choose, again, a value for X that will help me cancel stuff. So I'm going to choose X as 1. And for this last substitution, I've got 2 of the values. I've got A and I've got C, so I can plug those in as well. So I'm going to box this because we keep coming back to that upper one as my kind of home base. 1 equals A is 1/5 times 1 squared plus 4 and plus B times 1 plus C is 1/5 times 1 plus 1. And this will allow us to solve for now B. So let's reduce this down. I've got 1 equals, so this is going to be 1 squared plus 4 is 5. 5 times a fifth is 1. And then I've got a 2, so I'm going to distribute the 2 to the B, so 2B plus 2 times 1/5 is 2/5. If I subtract my 1s, they're going to cancel. Subtract over 2/5, I'm going to get negative 2/5 equals 2B. Divide by 2, I'm going to get B equals negative 1/5. And with that, we're ready to plug back in and integrate. So we'll come back up to here. Again, we rewrite to make the integration easier. So this is now going to be the integration of 1/5, that's my A, over X plus 1, plus B is negative 1/5, X plus C is 1/5 over X squared plus 4 dx. And so at that point, I'm ready to now run my integration. So at this point, I'm going to let that 1/5 that I plugged in for A just rest as a coefficient, 1/5. And then as we'd seen with our previous examples, if I've got a differentiation 1 over X plus 1 dx, the antiderivative is going to be the natural log of X plus 1. So that helps me integrate there. Now for the integration on this next one, I'm also going to factor out a negative 1/5. And what that's going to leave me in my numerator, if I just write this here, it's negative 1/5 times X minus 1 over X squared plus 4. So just thinking about the integrand in that format, if I've got X squared plus 4 as a U, so we're going to do a little substitution here. U is x squared plus 4. In that case, du is going to be 2x dx. So I've got an x. In fact, what I need to do is I need to separate that fraction. So before I go into all this, I need to, in a way, rewrite this. So right below, I'm going to pick up here the integration. And what I'm going to do is take the negative 1/5 outside. And then I'm going to split this fraction up. So it's going to be x over x squared plus 4 minus 1 over x squared plus 4 dx. So I do have to do one final rewrite here to evaluate this second fraction that we wrote, the one that's bx plus c over x squared plus 4. So that's ready now. I can use my u substitution here. I've got the 2x. Well, let me just mark what I got. I got x and dx. I do not have a 2, so what I need to include is a 1/2 to cancel that. So as I set up my integration, that's going to be that half. And then it's going to be 1 over u, so that's going to be natural log of x squared plus 4. And then to integrate my last component there, I'll put my plus 1/5, negative 1/5 in fact. And then this version, let me highlight it here in yellow. That is a different setup. And what that matches, if I'm thinking about antiderivatives, if I've got x squared plus, in fact, 1 over x squared plus 4, that, if I search for an antiderivative, is going to come from the inverse tangent of x. So setting that up for the final integration here is going to be the half times negative 1. In fact, what I need to do is I need to resolve this sign. It's minus instead of plus. And it's going to be 1 over. In fact, let me write my rule here. It's going to be 1 over a tangent of u over a. And let's identify my u and my a. This 4 is a squared, so a is going to be 2. And my u squared is x squared, so my u is going to be x. So for mine, it's going to be 1 over 2 inverse tangent of x over 2 plus c. So I probably need to rewrite that integration all in one row. So what we'll do is we'll pick it up. It's going to be equal to 1/5 times the natural log of absolute value x plus 1 minus 1/5. In fact, let's call that 1 over 10 times natural log of x squared plus 4. And we would finalize that as plus 1 over, I got a 5 and a 2 and a 2, so that's 1 over 20 inverse tangent of x over 2 plus c. That is a long answer, but it is complete. And we'll box it there. Thanks for joining for this investigation of integrating using polynomial long division or partial fractions. See you soon.